Hello, this is Dr. Lori. Welcome to this next video looking at some of the assumptions and the central limit theorem. Before we get started with that conversation, I would like to do a really quick review, and this will lead into what we're talking about in terms of the assumptions. So, first of all, we have looked at standard error, we've looked at confidence intervals, we looked at the critical ratio, um, all of those kinds of things. And what I'd like to point out is that sample size really has a relationship with all of those different concepts. As we increase sample size, do you remember what happens to the standard error? Really quickly, standard error is equal to the standard deviation divided by the square root of n. Sample size is n. And so if n increases and it's on the bottom of the equation, then standard error is going to decrease. So as sample size goes up, or n goes up, then my standard error goes down. In other words, my distribution is narrower. And that ties into this second thing, which is the sample size. As the sample size increases, my confidence interval gets narrower. And that makes perfect sense because of this. If I have a distribution and the width here is 2 times the standard error, actually it's 4 times. Here's 2 SEs minus 2 SE and plus 2 SE. If my standard error gets smaller, then the width across for that 95% confidence interval also gets narrower. Another thing happens with the t or the critical ratio. As my sample size increases, that impacts my t. And remember, t is calculated as x bar minus mu divided by standard error. And if my standard error goes down, then my t value is going to go up. So as sample size goes up, my critical ratio also goes up. That has a direct impact as t goes up. That also impacts our p-value. P-value gets smaller and smaller and smaller the larger t is. And so really all three of these things are related to the same concept. They're all related because standard error gets smaller, whatever my statistical value gets larger, my p-value gets smaller. They're all interwoven. This other concept, the new thing that I want to talk about, is that as we increase n, as we increase sample size, another interesting thing happens, and it does not have to do with how spread out they are. All of these have to do with how far spread out they are. So the standard error is spread. The confidence interval is spread. The critical ratio is related to whether that hypothetical value falls within the spread. But another thing happens, and that is that as the sample size goes up, the distribution, the shape of the distribution becomes more symmetrical. So this is a shape issue. The central limit theorem is a shape issue. It's not a spread issue. So be just really, really clear about that. And I'll show you exactly what the central limit theorem is here in a minute. The fact that this is more symmetrical is really good news. And that is because one of the assumptions of performing this t-test or a z-test or a lot of the different kinds of tests that we do is that the sampling distribution of the mean, that's not standard deviation. Let me clarify that. SD usually means standard deviation. The sampling distribution of the mean needs to be normally distributed. And as our sample size goes up, that is more and more likely to happen. So let me show you just really quickly why this matters. Let's say let's just take an example. Let's say that our sampling distribution of the mean is shaped really weird. Let's say that it's extremely skewed. If we were to put our mean in any given location, then what happens is we try to go, let's say we try to go 1, 2 standard errors away and 1, 2 standard errors away. We end up with that confidence interval, and it's not capturing the percentage, that 95% confidence interval, correctly. If the shape is not symmetrical, if the shape is not a normal distribution, that normal bell-shaped curve, we need it to be that normal bell-shaped curve in order to make those conclusions that we made, that there's 2.5% in each tail, those kinds of things. And the magic of this is that as soon as we have an n of 30 or more, of at least 30, what happens to any kind of a skew is that that tends to start disappearing. So if we have an underlying population that's skewed or has leptokurtosis or platykurtosis or some strange bimodal distribution, as we create this sampling distribution of the mean, as soon as we have about a sample size of 30, then our sampling distribution of the mean becomes essentially normally distributed. That phenomenon of becoming the right shape for us to use for this hypothesis testing is called, wait for it, the central limit theorem. So basically, what we learn from that is as soon as I have a sample size of 30, that at least one of my assumptions for statistical testing, so running a t-test or different kinds of things like that, a one sample t-test, that assumption is met. So if the sample size is less than 30, then we have to really be careful about that. We can see that there are more than that this increase in sample size impacts both the spread and the shape, and indirectly it, in a way, because this confidence interval gets narrower, basically what that says is that the larger my sample size, my x bar is going to be closer and closer to mu. I'm going to be more and more sure of my location. So indirectly we also have the increase in sample size improving our estimation of the location. So having a larger sample size can be a good thing in a lot of different ways for our statistical testing process. So thank you for joining me for this review.